Hey guys, welcome back to our third recording for our skeletal chapter here in Anatomy and Physiology. Today I'm going to take you guys through how we form bone, how bones are broken, how they're healed, and then in our next video we will actually start naming bones and their structures for the whole skeleton. So let's jump right into it here. How do you form bone originally? Bone growth, when you are a little baby, a little embryo still forming in utero, you are going to replace connective tissues. And there's a couple of ways we're going to do this. So the first way we can do this is going to be found in your skull, in the intramembranous ossification. So intra means within, membranous means membrane, and ossification is forming bone. And so what we get is, to form a little fetal skull, we lay out these sheet-like layers of connective tissue. And then within that connective tissue, there are little cells that will differentiate into osteoblasts and start to lay down bone matrix. And as they lay down bone matrix, what was a rather soft sheet-like layer starts to become a flat bone in your skull. First, these guys will form a spongy bone. After that, they'll form the outside layer, which is the periosteum, and then we'll fill in that remaining gap with compact bone. So you do not have to take the steps and commit those to memory necessarily, but you do need to know what intramembranous ossification is and where we use it to make new bone. So our osteoblasts are going to eventually completely enclose themselves with bone matrix, and they've formed their own lamellae, or rather lacunae, when they do this, and then we call them osteocytes. And now we have a hard, bony structure that we can use to build the skull. So you use this to build broad, flat bones, like in the skull, with the exception of the mandible. Mandible is not built this way. So intramembranous ossification is cool, but that only covers the skull. We need to look at how we build all of the rest of the bones in tiny human. And so that takes us to endochondral ossification. Endo means within. Chondral, you might remember chondrocytes were cartilage cells in our cartilage. And so ossification is the formation of bone. So this means the formation of bone within the cartilage. And our bones, your long bones, begin as hyaline cartilage, and that lays down the framework that we will later build to shape future bones. And so when you are a teeny, tiny little developing embryo, you are made of a framework that's about as flexible and tough as the end of your nose, if you recall where we find hyaline cartilage. So a pretty flexible framework. And then we lay down bone material within that, and most of the bones of your skeleton are going to be formed that way. So the cartilage grows into the shape of, a new little baby. The cartilage breaks down in that diaphysis, and it disappears as that periosteum develops around the diaphysis. And so we're not necessarily starting from within this time. We're starting around the outside of the bone. And then slowly those osteoblasts and vascular tissue like blood, we're going to replace that cartilage framework with our spongy bone. And that's called a primary ossification center, or the first place you start to make bone. And as the bone continues to grow, we lay down compact bone, and now the bone is actually pretty strong. It's still a little bit flexible, but it's pretty strong. And we start in the middle of the bone, pardon me, and we work our way towards the ends of the bone. And so that's how you lay down bone tissue for endochondral ossification. Again, do you need to be able to list each step from memory? No. Do you need to know how we form long bones when we're teeny tiny little babies? Absolutely. So that's one way to build bone. Growth continues in the epiphysis area, so the end of the bone, and it's not complete, of course, until that growth plate is closed in your teen or early 20 years. And now that you know that bone is formed from a cartilage framework, you understand, of course, why the growth plate, the epiphyseal plate, exists as a young adult. It is the leftover cartilage from when you were a teeny tiny little baby developing those bones. So that's kind of a cool way to know how your bones are formed. Eventually, our secondary ossification centers appear, and our osteoblasts lay down spongy bone, and by the time it's all done, we have, you know, the end product of a radius or a femur or whatever we were growing. So growth continues in the epiphysis. The secondary ossification center appears. That's where we left off last time. Osteoblasts lay down spongy bone, and we end up with our epiphyseal plate, which is this little bit of cartilage, which we call the growth plate. So the cartilage eventually dies. It eventually becomes bone, and when it does that, you are done growing vertically. Growth continues until the epiphyseal plate closes. You might have heard this called the growth plate closing or the growth plate sealing, or if you break your ankle in high school, it might be a concern that you've cracked a growth plate. That's what they're referring to, is that epiphyseal plate at a young age has not ossified yet. So we do end up with a medullary cavity in these long bones, so where the bone marrow is stored. That's the result of the work between the osteoblasts laying down new bone material and the osteoclasts digesting bone material. And so here's what it looks like. What are we making here? We're making a femur, okay? So teeny tiny baby femur, and it's flexible and it's soft and it's cartilage, right? We get a periosteum starting to grow, and we get a little bit of bone material starting to grow here. As the bone develops, it starts to take a little more shape. We start to get some growth centers here in our epiphysis, and at this point we're starting to form a little bit of a medullary cavity. We feed a little bit of blood into this, which makes the growing so much faster. It's almost incomprehensible how quickly you grow when you're a teeny tiny little fetus. It's pretty amazing. And we get our secondary ossification centers laid down here in the epiphysis, the proximal and the distal. We're getting a pretty well developed compact bone here and a pretty well developed medullary cavity here. We're growing, and we are, born at this point, I would say, because we've got some pretty good cartilage, some articular cartilage here, and our epiphyseal plates are looking pretty good. So this is a growing kiddo now. They still have a good blood supply, and they're still growing. And then this is the adult. They have a much longer femur. The epiphyseal plates are now reduced to really just a little line of bone that's barely visible, and this is as tall as this femur will ever be. The medullary cavity runs pretty much the whole length of the shaft of the bone or the diaphysis, and that's a done deal. That's an adult bone, and it all started from this little rectangle of cartilage, which is pretty cool. So I've got a video I'm going to show you for this, so hang on tight and enjoy this, I guess.
During embryonic development, cells called chondroblasts begin secreting cartilage that develops in the shape of the skeleton's long bones. The bluish, transparent avascular tissue formed is called hyaline cartilage. As the cartilage grows, the chondroblasts in the interior calcify and die. Blood vessels penetrate the structure and deliver osteoblasts. These cells lay down bone material. As the cartilage ossifies and spongy bone forms, a medullary cavity develops. At the ends of a long bone, ossification from cartilage also occurs. This process, in which hyaline cartilage becomes bone and grows, is called endochondral ossification. Bone growth continues through childhood. After puberty, bone tissue replaces the remaining hyaline cartilage, and the shaft reaches its adult length.
So there you go. A much more nicely animated view of what we just talked about there. So I hope that was helpful. All right, so here's just little bullet points for what we just talked about and what that video just talked about as well. All right, so more about growth at the epiphyseal plate. This is just, we're zooming in really close on the epiphyseal plate here, which is our first layer of cells start at the closest to the end of the epiphysis, and we call these resting cells. And then the second layer of cells have a lot of younger cells that are undergoing mitosis and growing quickly, I guess you could say, from the epiphysis out, or from the epiphysis up if it's the proximal one. So they're going to grow away from that growth plate basically. And then our third layer of cells here, these are a little bit older cells. They're starting to become calcified. And then we have our fourth layer, our pretty thin dead cells right here. So new cells, growing cells, ossified, and then osteoblast depositing bone tissue. So this is the bone. That's the epiphyseal plate, the cartilage. And so we are growing, I guess, down the femur in this example. And that's just the process of these cells dividing, making new cells. And once this is gone, then we are as tall as that bone can be. So that's kind of cool. You don't by any means need to break these down into 4 steps and memorize them, but just kind of understand that it grows starting at the epiphyseal plate and grows away from the epiphyseal plate, and you'll be in pretty good shape. So a little note about homeostasis in bone tissue. This is a really cool picture of that medullary cavity just starting to develop, and some osteoclasts here eating away at the bone material that would be there. So they're making that medullary cavity, which is kind of cool. That bone tissue is continually remodeled throughout the life of the organism. As long as you're alive, your cells, your osteoclasts are eating away bone material and your osteoblasts are laying down bone material. It is regulated by a variety of hormones. We'll learn about all that in chapter 13. And 3 to 5% of the calcium in your bones is exchanged annually. So this is always changing. And so here we have these guys eating away the bone to develop this medullary cavity. It's a cool example of osteoclasts working. So there's a couple of cool terms. There's resorption and deposition. And so bone deposition is depositing new bone matrix, which makes more bone. And that is osteoblasts working with a hormone called calcitonin, which helps take calcium out of the blood and put it into the bone. The opposite of that is bone resorption. So the action of osteoclasts and parathyroid hormone work to break down bone tissue and get that calcium back into the bloodstream. And so these two guys are opposing forces that keep us in equilibrium, more or less. So real quick, a cool picture of how we can heal a broken bone. Broken bones heal very, very fast, so much quicker than a torn tendon might. In a young, healthy person, bones can heal. It's crazy how quickly they can heal. So healing fractures, if you break a bone, there's a few steps we're going to do to get this thing healed up. Number 1, break the bone. Number 2, blood vessels in that bone that ran up and down the marrow and all over, of course, inside of the microanatomy of the bone that we learned about, central canals, perforating canals. When you break the bone, you break those blood vessels. So a lot of blood can be released from a broken bone. Now, that's okay because it gets a lot of white blood cells there and it gets a lot of platelets there, but we got to stop the bleeding before we can do anything else. So your body's going to form a blood clot or a hematoma, and that's going to be right here. This shows the hematoma as this whole red clot that's kind of bulging out away from the break. So step 1, stop the bleeding. Step 4, surrounding blood vessels are going to dilate. They'll actually become larger to cause swelling. Now there's a variety of reasons for that, but one of them is if your arm is swollen, you know there's something wrong with it. It hurts to move it. It adds a lot of heat and blood to the area so it can heal faster. There's a lot of reasons for swelling, but if you break a bone, the limb is going to become pretty swollen where you broke that bone. So then we have osteoblasts come in, and they're going to attack that hematoma because we can't just have this giant blood clot hanging out forever. That's not going to be okay. So the osteoblasts and blood vessels are going to take that hematoma and digest it, take that hematoma away, and they will start to lay down some spongy bone. Remember, osteoblasts build bone, so they'll lay down spongy bone. It's not real strong yet. You probably shouldn't be out swinging a baseball bat or walking on it, and that's why we put you in a cast. But they're going to lay down that spongy bone, and that can happen really within a few hours after the break. We can form a hematoma, digest the hematoma, start laying spongy bone. It's quick because there's a lot of blood available. So 6, granulation tissues and fibrocartilage are formed. And so what we end up getting are a bunch of tissues inside of here that are going to support and scaffold this until the bone is completely healed, and that's the fibrocartilage piece. Phagocytes are going to eat away that blood clot, and the osteoclasts are going to remove bone fragments that might still be there from the break. And when it's all done, what you'll actually get is the place where you broke that bone is larger than the rest of the bone. It kind of continued that swelling from the original break. The periosteum is actually much bigger. and the rest of the bone matrix is much bigger. So the likelihood of you breaking that bone right here again is significantly diminished. You could still break this bone. You could break it here or here, but probably not right there, because your body has adapted to what was a lot of stress on that bone. So that's kind of cool. And when all that's done, it's healed. It's a done deal. You take the cast off and you can walk around, play baseball, and all that kind of stuff. So fibrocartilage fills in the gaps. Cartilage breaks down as the osteoblasts build bone, and once all the bone's filled in, that's a done deal. So with that, we're going to go over types of fractures, and we're going to call it a day. There are a few different ways you can describe a break, and it depends on the angle that the break occurs at, and a few other factors. So the first type I want you to know is called a green stick fracture. A green stick fracture is incomplete. This bone was not broken all the way through. And they call it a green stick fracture because if you take a stick from a tree that the tree is alive and you flex it, it's very hard to snap it all the way through. Like you can, a dry twig just breaks right in half, but a green one will just break the edge. You'll see this a lot in young kids. Young kiddos still have pretty flexible bones. So under a lot of stress, that bone will flex and bend a lot and then just break at the end a little bit. And that's why we call it the green stick fracture. Next one's called fissured. The fissured fracture is a longitudinal break, so it runs up the length of the bone or with the direction of the bone. This is a tough one. I always say this word wrong because I just love the word comminuted, but it's wrong. The way you say it is comminuted. Comminuted. A comminuted fracture is where we break this into little teeny tiny pieces. Okay, this will heal pretty easy. This will heal pretty easy. This thing can be kind of a mess, depending on how bad the fracture is. This could be, potentially amputation. It can be so bad, but basically you can't form that swollen periosteum and blood vessel clot because there's nothing to form it around. You've busted it into just pieces. It's just a puzzle now, and that's a bad deal. We see that here in South Dakota, around the motorcycle rally. Someone will tip their bike over, and that turns out those Harleys are kind of heavy, and what used to be their femur or their tibia just gets crushed into a bunch of little pieces, and it stinks, but it's kind of, those can be a real trick to get those to heal up. So that's comminuted. Here's the one you're probably going to see the most. Transverse fracture. This is very typical. Forces coming this direction at the bone, which is, I think, the majority of your breaks. Is the force coming not with the bone, because bones are good at resisting crushing, but when the force is coming, I guess from the side of the bone, you're going to get this transverse fracture. That's your standard, kid trying to jump off of a deck or injured playing sports or something. This force is coming at a tangential angle, maybe, to the length of the bone. And so what you end up getting is a right angle break on that bone. That's pretty common, and they'll heal up pretty quick. Oblique runs at an angle up the bone. You think the oblique muscles are these muscles in your body that run down at an angle along your abdominal region, and the oblique fracture runs down at an angle along a bone. And then finally, the spiral fracture, twisting a bone excessively. They're not super common. I've only heard of a couple people that have got a spiral fracture, but basically this bone, you can see this side, this is the front of the bone here, and this is the back of the bone. So this bone was grabbed by something or someone and twisted and broke from that twisting. And so that's kind of that's a sad thing to see, but it can happen from all sorts of different things. So that's a spiral fracture. So there's your different types of fractures. And I think that is where we are going to stop for today, because the next time we're going to come back, we're going to look at the skull and start naming bones. So thanks for your time.